Hello, so now we are back and we want to solve the second assignment which is given to us for the binary search tree. And in that case, we are going to be solving the first problem, which is given the root of a binary tree. Check whether the binary tree or not the binary, binary tree is a BST or a binary search tree or not. And to do that, we can create a very simple recursive function for that. But before that, I want to tell you that in the binary search tree.c file, we do have a couple of helper functions which will be made use of in the problem number 3 and 7 and other problems as we go and move forward. And remember, there are going to be cases where I'm going to be using the limits.h. So understand the logic for int minimum and int maximum. The logic is very simple, which is basically you have a maximum capacity for your integer variable like data type. And in C, if you have a 64-bit system, you basically allocate 4 bytes of data to an integer, and that means 4 times 8, that's 32 bits. Keep 1 bit for signed integers for signness, so signed bit. So if that's the case, then basically you have 2 to the power 32 bits for your negative and your positive, and in your positive you do need to count for 0. So that leads you to a maximum value of 2 to the power 31 minus 1. That's the answer for your int max. Where is the int max? Here is the int max, and this is expands to this value, and int minimum basically expands to this value. Now, if that is done, now what we are going to do, first we need to understand how the helper functions basically work. Basically, they create the binary search tree with the same logic that is here in the assignment. As you can see, you have a node. Then based on this node, suppose the left and right, okay, I think this is a given a binary tree, probably. Yes, it is, or I think there was some kind of typo, no? Okay. We probably can't use this example that much. So what happens generally in a binary search tree, you have the left node which is less than the root node, and you have the right node which is greater than the root node. And that's the logic for binary search trees. That's it. Very simple. Now, if you have this root node being equal to null, you just basically you don't have anything, you're at the beginning of the universe, you just create the node. If you're not at the beginning of the universe, what you need to do is basically you have to check if the given data that you want to insert into the binary search tree is less than the root data. If it is less than the root data, you basically just call the binary search tree again. Why? Because you now have something on the left, right? So you can't be like overriding the data. So you just call it, pass the left node, and then you just go forward. Do it till you reach the child node where you don't have anything. Basically, suppose it is 7, then on the 7, as you can see, we are basically 7 means it is also not null. But as we go here, the child of the 7, you can see that there is nothing. So here is the beginning of the mini universe, maybe, whatever. So there you just create the node, that's it. And you create the node and you just return the node, and that's it. You link, of course you do the linking and everything. It is already linked, so you don't need to worry. But what happens, you basically create another node where suppose it is this is not a good example because this is basically not binary search tree. So 3 should be here, like 7, then 3 should be on the left side. Say 19 or 20 is there, then 20 will be on the right side. So with that case, you just create the binary search tree, and then we just go into the first problem, which is here. So in the first problem, we need to check, given a root of a tree, basically if that tree is a binary search tree or not. So I need to first understand that I need to have 2 specific values, basically negative infinity and positive infinity, to understand to do the iteration, or not iteration, recursive calls. And we don't have negative infinity or positive infinity in C language. So what do? We do the maximum limits which are possible, which are int min and int max. So now if you have an empty tree, basically you just return true, because an empty tree basically means there is no compare. An empty tree is basically a binary search tree. It is a binary tree. It is whatever tree you want to give it, make it. Okay. Now if the case will be if the node's data is less than the minimum value, or if the node's data is greater than the minimum value. That means the current node that you are on, maybe the root node, maybe some other child node, your value is going against the range or the minimum value or the maximum value possible. Then of course this is not a binary search tree. Now we need to do the main iteration. Here you are going to see that we are going to be changing a few instances of the code. So instead of int min and int max, we are going to be changing them. But how we are going to change them? Suppose you are on the left node. Okay, so everything passes here. Now suppose you have something, I should have just opened up a good example. Let's do binary search tree examples and go to an image. Let's take this for a name. So let's open up in a new tab. So as you can see here, we have 25, and from 25 you can see 20 is less than that, 36 is greater than 25. So this is a good binary search tree example. Now what happens that you pass a node, 25 is passed, it passes to all of these checks. Okay, that oh yeah, by the way, it passes through this checks because it is of course like not of this, so this is fine. And then is the BST util is again calling 25's left node, so that's 20 here, and basically 20 not the value but the node itself, so it's passing all the information along with it. Then basically passing the left subtree here. Next, instead of the minimum value, okay, you can see the minimum value, we are again passing the int min, which was set to be the minimum value. So this thing hasn't changed. So the minimum value is still the negative infinity or the negative 2 1 something, basically negative 2 to the power 31. And instead of the maximum value, we are passing the node data. That means what? That means this node's data is 25. So at max, the left subtree can, the starting of the left subtree can at max be 25. Okay, so I said 25. Yeah, it should be 25 because we in this checking we are allowing that equality, but it's a weak case. You might want to, you might not want to, but what happens if you do allow the equality, then here it gets taken care of, so don't worry. This is during insertion, so you can't do that. So that's why this helper function was explained in the first case. Now if that is the case, what happens that you are allowing 25 to go there, then you just do 20, so it can at most go to 25. So the next value that needs to be checked is basically the left node, and then it goes here in the minimum checking function. If the node's data, that is 20, is less than the minimum value, remember we did not change any minimum value, so this condition is basically false. But here the thing that we need to check is the value of 20 greater than the parent, which would be what? Which would be if that is true, then of course it is not a valid binary search tree. And this is the case where it if it were not a binary search tree, it will fail and basically return a false. And but it is going, because of course this condition is itself false here, so it's not going into the if statement. Then it goes to the return statement, and then again this goes through the binary what do you call this, the left subtree, and it goes to till like, and then again goes from 1. Then after that, because after this both of them are null, you go to 5 and then do the 8 and then traverse the right subtrees. Then you go to 36, and then 36 is the right subtree of the beginning, so root. So then again go 36 ka jo hai left mein jao, then it goes to the right, and that's how this whole journey goes on till it checks every node that is it a valid binary search trees if it follows the binary search trees conditions or not. With that, the problem number 1 is now here done and dusted. Thank you. And I don't know if I said subscribe, but if you want to, you can, or if you don't want to, whatever be your wish, enjoy your life.